Hello everyone, and thank you for listening in. If you're watching this in session, this is just before 6 a.m. my time, and I hope I've had enough coffee to be able to answer any questions you might have at the end. I'm Alison Troop, a geoscientist from Brisbane, Australia. I'm currently studying for my PhD at the University of Queensland, and while this sadly does not relate directly to my project, it's come about from some seismic interpretation work I completed for another project while working for the Geological Survey of Queensland. Now, I'm primarily a petroleum geologist and sedimentologist with an interest in regional interpretation and basin evolution. Sometimes seismic interpretation identifies some surprising and unexpected features, and who doesn't love a potential impact structure? I'm here today to discuss some observations from 2D and 3D seismic in Central Australia, and what appears to be a small, simple impact structure on the margins of a much larger complex crater that impacted during the early Cretaceous. This new structure is tentatively called the Tintaburra structure after the oil field in the area. We're going to spend the next 11 minutes or so in the early Cretaceous of the Eromanga Basin in central to eastern Australia. The Eromanga Basin is a large intracratonic basin in Central Australia that covers approximately 385,000 square miles, or around 1 million square kilometres. The lower units of the basin are dominated by fluvio-lacustrine units, with a gradual transition up sequence to marginal marine units by the early Cretaceous, and marine units in the Wallumbilla, Tookoonooka and Talundilly formations. From the Wyandra sandstone, here, down on the stratigraphic chart, many of these sandstone-dominated units, the ones in yellow, are oil reservoirs in the Eromanga Basin, and petroleum exploration in the region has provided the data necessary for this interpretation. The boundary between the Cadnawi Formation and Wallumbilla Formation is marked by a consistent seismic reflector, the sea horizon, which can be mapped in basins of a similar age across Queensland. In most areas, this horizon is sharp, flat, and very easy to recognise and map. However, in the south, there's a region of significant disruption to this horizon, which is associated with a large confirmed impact structure at Tookoonooka. This image shows the broad regional interpretation of the sea horizon across most of the basins of eastern Australia of this age. This is what the sea horizon usually looks like in the top, and marked by the horizon at the orange arrow. It's generally unstructured and a very clear marker horizon in seismic, and I know that it was the first horizon I learnt to identify at a glance when doing seismic interpretation. It's incredibly consistent across long distances, except for the area in the south near Tookoonooka. Now, in the south near the Tookoonooka impact, there's a significant disruption of the sea horizon. Most of this is either draping or broad-scale folding, although some authors have described it as tsunami-ite deposits resulting from the Tookoonooka impact. The Tintaburra structure sits just outside the radius of the Tookoonooka crater on top of one of the broad-scale folds in the sea horizon and appears to impact the same horizon. According to the Earth Impacts database, there are 6 features that define an impact structure: shadow cones, planar deformation features, high-pressure polymorphs, the shape, presence of impact melt sheet or dikes, and pseudo-tachyllite or breccias. The first 3 are diagnostic of the impact of an impact structure, while the last 3 are indicative, but require more work to be done. We're going to be focusing on the morphometry and morphology, as well as the geophysical signature of the Tintaburra feature in magnetics and seismic imagery. The Tintaburra structure is buried under 700 to 800 metres, approximately 2,200 to 2,600 feet, of early Cretaceous marine sediments in the Eromanga Basin of central and eastern Australia. As such, there is no outcrop and limited samples, so this interpretation is reliant on geophysical data, but it would be great if anybody would like to help me follow up on this. I've got some more recommendations at the end of the talk. So because it's undercover and we're reliant on the shape and geophysical character, it's good to quickly review the kinds of features we'd expect to see in magnetics, gravity, and seismic signatures. Unfortunately for buried craters, there are no definitive geophysical signatures that confirm an impact origin. Some craters do have magnetic anomalies, like the 3 we'll discuss today. Most authors note that a negative gravity anomaly is expected, which none of the ones we'll discuss today have. Seismic imaging highlights the structural disturbance and can help to provide the morphometry and morphology of a crater, but it's not diagnostic in itself. One thing that should be consistent, however, is that impact anomalies would be expected to be circular or nearly so, though this could be affected by erosion or by low ankle entry. There's a bit of a challenge for interpretation on gravity or magnetics data for this region, as the only surveys are broad regional grids. Gravity is particularly affected by this, so we're going to disregard that for now and focus on the magnetic anomalies and seismic interpretation. For a little bit more regional context, onto the big structures. The Tookoonooka impact structure is a confirmed impact crater with a complex character when examined in seismic. It was of particular focus when identified on seismic early on in petroleum exploration in the region, when petroleum explorers targeted the central uplift as a hydrocarbon trap. The timing of the impact event is at the Birimian to Aptian boundary at around 125 plus or minus 1 million years ago. It has a crater diameter of approximately 66 kilometres or 41 miles, making it the second largest crater in Australia and the 10th largest impact structure in the world. Talundilly is not as defined as clearly, as it has fewer wells drilled in the region and fewer seismic surveys, so it remains a possible impact structure, with a diameter estimated at 95 kilometres from seismic, likely the apparent crater diameter, and a final crater diameter closer to 30 kilometres on more recent interpretations. These two craters have been interpreted to be a twin impact structure, where the original bolide has separated or was originally a binary asteroid. The map on the left shows the location and uncertainty in diameter of the Tookoonooka and Talundilly structures, based on work presented by Bron and Gostin in 2012. The map on the right is the total magnetic intensity map for the region, showing the stark magnetic anomalies for Tookoonooka and Talundilly. At this scale, the Tintaburra structure is barely visible inside that little green circle, but it sits here, quite close to the Tookoonooka magnetic anomaly. Now, one thing is interesting is that you can draw a line between Tookoonooka and Talundilly, and Tintaburra sits along it, suggesting that it might be somehow associated with the same impact event. Zooming in further, we can see Tookoonooka's magnetic anomaly here, and the much smaller anomaly at Tintaburra here. The final image on the right is zoomed right in on Tintaburra's anomaly, while showing the 2D seismic coverage in the region. While this is a regional magnetic interpretation, the Tintaburra structure has a roughly circular anomaly in the magnetics, if 17 or so pixels at this scale can be considered circular. Don't worry, it'll get rounder in the next few slides. This is seismic line EH8405 from the Gorter seismic survey, with the interpreted base Winton in green, Wallumbilla Formation in yellow, and the sea horizon in blue on the top image, and an uninterpreted version in the bottom image. In this seismic line, the Tintaburra structure is a bowl-like depression, affecting the sea horizon. At its base, you can see better in the uninterpreted image, there is a section of what appears to be brecciated rock. This is a fairly shallow structure on these surveys at just over 100 metres or 300 feet deep. It does not appear to have penetrated far enough to affect basement. I haven't mapped the faults in these interpretations, however you can see slumping and faulting associated with the edges of the structure in the overlying units as well as where it's impacted. Unfortunately, the intersecting lines in a Gorter seismic survey did not image this structure particularly well. However, we are fortunate to have 3D seismic over the area, which enables not only the examination of the inlines and crosslines, but also of the Z or time slices to examine the morphology of the structure. This figure is showing the structure on 3D seismic with one inline and one crossline from the Tintaburra 3D seismic survey, showing that it's still bowl-like in nature and affects the sea horizon, which is this level coming across here. When we take a Z slice at a time that is very close to the top of the sea horizon on either side of the structure, showing the Z slice with the two seismic lines from the previous slide for orientation, and we find a nice circular anomaly at approximately 612 milliseconds. From this seismic, we can estimate the size of the structure to be 700 to 1,000 metres in diameter and around 115 metres deep, based on a velocity of 2,100 metres per second from a nearby check shot. For a visual, this is just a bit smaller than the Barringer crater in Arizona. So we have a small potential impact structure with a magnetic anomaly and bowl-like shape in seismic. Based on the seismic horizon it disrupts, it has an impacted at a similar time to the much larger Tookoonooka structure and the potential Talundilly structure. This suggests that the three structures together could be a triple impact event, with Tintaburra forming from a smaller fragment of the bolide. However, as it's relatively close to Tookoonooka and as a marine impact, large tsunami waves and their associated erosion would be expected from the larger impact, which may either have affected the preserved size of the crater or provide a reason for Tintaburra to post-date Tookoonooka and Talundilly to be preserved like it is. There are still also the first three diagnostic characteristics to figure out. If anyone wants to collaborate on this, I seem to enjoy too much work. So here are my future recommendations. Sampling of core to create thin sections for examination of planar deformation features. Examination of core and sidewall core for brecciation, and using XRD to test for high pressure polymorphs. However, there would be a challenge in teasing out responses specific to the possible Tintaburra impact from the much larger and nearby Tookoonooka impact, as there's already shocked quartz in the area, and trying to determine which impact it's from will be difficult. Finally, if there's a physicist around who might like to look at whether a triplet impact structure might make sense from an orbital point of view, I think that could be a really interesting approach. Thank you very much for taking the time to listen, and my email address is on screen and my Twitter is also there if you would like to discuss any of this further. Thank you.